familiar to some in the audience, and so I will spend quite some time on the classical part of this application, and then toward the end I hope to be able to say something about the new results from this work. So let's start with graphs. Even before going to association schemes, this is the Patterson graph, a rather famous arrangement in combinatorics. It has 10 vertices and it is 3 regular, so to every vertex we have 3 edges attached. And more can be said about this graph, namely, if we take any pair of adjacent vertices, then they have no common neighbors. So these red vertices have no common neighbors. And we can go around the graph and it persists. So any pair of adjacent vertices has no common neighbors, never mind which pair we take. But if we take a pair of non-adjacent vertices, such as these two, this red one and the other red, they do have a common neighbor. And this again persists throughout the graph. So we take this pair of non-adjacent vertices, they do have a common neighbor. Right? And so the graph overall is called strongly regular. It is on 10 vertices, degree 3, no common neighbors for adjacent, 1 for every non-adjacent. And this is quite a topic in combinatorics and algebraic graph theory. There is a book in some part devoted to this story, and there are other books, so strongly regular graphs. From there we can make a next step about regularity in graphs. And for that I took another example, so let's consider the Hamming graph. This is the graph of the Hamming space of dimension 3, so the vertices are labeled by binary vectors of 0s and 1s, dimension 3, three-dimensional vectors. So we start with 0, 0, 0 here, and then vertices with 1, 1 and 2 zeros, 2 1s, 1 0, and then 1 1 1 finally. So obviously we get a complete graph on 8 vertices, K8. And now let us partition this complete graph into subgraphs related to the Hamming distance between the vertices. So the blue vertices, the blue edges now show distance 1. If we go from 0 0 0 to 0 0 1, this is one Hamming step, and so we have a blue edge, blue, blue, and then from 0 0 0 to 0 1 1, it is 2 Hamming steps, so we have a red edge, and finally 3 Hamming steps. Those are the green edges, the 4 parallel edges that connect vertices at this Hamming distance 3. Now this graph of course is regular as before, but more can be said about regularity. Namely, I'm claiming that if we take any edge, red edge, such as this one, and try to count the number of triangles with this as a base in the graph, and let's say the triangles have both other sides red, so this is one and then this is the other attached to this red edge, and then I go to another red edge such as this one and again count the number of red triangles, one red triangle, the other red triangle. So whatever red edge we take, there are exactly 2 all red triangles. And this picture is the same if instead of all red I will consider, let's say, blue, blue. I have one, I have another, and then from this red edge I have one triangle with both blue sides, and somewhere there should be the other. Oh yes, this one. And so the count of triangles depends only on this with sides of particular color, depends only on the color of the base. It does not depend on the specific choice of the base. Right? So this high regularity of triangles, a very powerful property really. So taking a blue, no, I'm going back, no, I'm going forward. All right, so the count of triangles is given by the color of the base, and so we call those numbers the intersection numbers of the graph. Pij, the base is of length k. Let's say a red base is distance 2, so k would be 2, and then I and j are the lengths of the sides. And Pijk does not depend on the choice of the vertices, but only on k and ij. Right? So this regularity is very powerful to be bypassed. So we are going to make use of this in constructing the concept, the structure of an association scheme. The first step will be to go from graphs to matrices. So let us have adjacency matrices of those colored graphs. We will have A0, so that is distance 0. Any vertex is distance 0 to itself, so obviously the adjacency matrix is diagonal. This is the adjacency matrix of the, the other way, of the blue graph. So going from 0, 0, 0 to vertices of Hamming weight 1, we have those 3 blue edges, so we have 1, 1, 1, and zeros elsewhere, and then A1 is filled as follows, A2, A3, we have 4 matrices, and let us observe some properties of these matrices. Namely, we have the sum of the AIs, of course, is the all 1 matrix. They're all disjoint and they fill everything. This is a complete graph. AI, AJ, this is the most interesting, in fact. So this exactly counts the number of triangles expressed through my intersection numbers. So I can express the product AI, AJ as a linear combination of AKs, and the coefficients are Pijk. And it is the same as AJAI. Well, so we're observing a commutative algebra, really, with respect to convolution, to the matrix product. And this algebra is also closed with respect to the pointwise product of matrices, the Schur product. Obviously, AI and AJ are simply disjoint, so this is delta IJ AI. Right, so this is a commutative algebra closed with respect to 2 multiplication operations that act in cohesion. That is a very powerful property that we can draw from the properties of the graph. So yes, 4-dimensional complex commutative algebra. Very well. Looking at this relation, it doesn't take much to convince ourselves that AI, the adjacency matrix of the ith graph, can be expressed as a polynomial of degree I, with the argument being A1, the first adjacency matrix. And another step will convince us that these polynomials, they satisfy a 3-term recurrence, and so they form a family of orthogonal polynomials. So to a graph, there are orthogonal polynomials that are attached automatically once we have this regularity structure. And in particular for the Hamming graph, we would observe the Kravchuk polynomials, a very well-known family of discrete orthogonal polynomials, both in harmonic analysis and combinatorics. Very well. This algebra, of course, is commutative, so there are common eigenspaces to all of those matrices, so there is a bunch of orthogonal projectors on those eigenspaces, and they form a basis of primitive idempotence of the algebra. So the idempotents satisfy properties similar to the adjacency matrices, but the Schur product and the matrix product are now interposed, as shown here. So this duality is another powerful feature of the structure that we are considering, and all of this we were able to derive from the structure of the Hamming graph. So obviously there is more to this, and now with this we can define finally an association scheme. And as we said, this is indeed one of the main concepts in algebraic combinatorics. So we start with a finite set, such as the 8 vertices in the Hamming space. We partition the Cartesian product of x cross x, x squared, into d+1 classes, R0 through Rd. R0 is a diagonal, and then if xy is in Ri, then yx is in some Ri prime from the same partition. This the second part of the definition. The third part of the definition is the count of triangles. Take xy in Rk, define the number Pijxy, that is the number of z's, such that xz is in Ri and zy in Rj. Then that number in fact does not depend on xy, but only on k, the count of triangles, and moreover there is this commutativity, and thereby we obtain a commutative association scheme. The notion was defined in the works of Bose and his collaborators in the 50s, and it was firmly established after the groundbreaking thesis of Philippe Delsart of 1973. There are many books devoted to this concept, Banai to algebraic combinatorics. This is another classic, distance regular graphs, and there are later books. In fact, perhaps 5, 6 could be counted easily after these classical and still useful books. Association schemes find applications, as we said, in graph theory, obviously, algebraic graph theory, coding theory, computer science, spin models, combinatorial models of statistical mechanics, and other areas that perhaps do not. Oh yes, also sphere packings. So indeed, this is one of fundamental concepts. Very well. As we said, there are 2 bases of those algebras. One is idempotence, the other is adjacency matrices, and of course Aj can be expressed as a linear combination of Ei's, the projectors, and conversely the same thing happens. Ej can be expressed as a linear combination of Ai's. Those things are indeed eigenvalues of the A's or of the E's, and they're called the first and the second eigenvalues of the association scheme. And in the polynomial case, the eigenvalues are expressed as evaluations of discrete orthogonal polynomials. So this is, oh yes, and another interesting step is to define an association scheme on a finite set which is at the same time a finite abelian group. In that case, the scheme is called translation. If we can take a pair xy in Ri, shift it by any z, and then we are still in the same Ri, so the abelian structure. And therefore, of course, it suffices to consider blocks in relation to 0. x0 is an Ri, and everything else is obtained by shifts. So thereby we obtain an abelian or translation association scheme, such as the Hamming scheme, indeed, because the Hamming space is an abelian group, addition modulo 2, coordinate-wise. And in this case, we can also consider the dual group of X, the group of characters. And on that dual group, we can define a dual association scheme. So abelian association schemes come in dual pairs, naturally, and there are other cases of duality that we will not discuss. So abelian are the most important for us at this point. For abelian schemes, the eigenvalues are easily expressed using the characters, and the idempotents are easily computed, so computations are made easy. So for the Hamming space, if you do this calculation, then indeed you will recover Kravchuk polynomial after 2 or 3 lines of easy combinatorics. Other orthogonal polynomials that come up, for instance, are the well-known Hahn polynomials, Gegenbauer or ultraspherical polynomials. And if you need to look for the tightest sphere packing in the real space Rn, then you would use this technique to derive the bound with Gegenbauer polynomials. So indeed, it finds many applications. Now, the starting point of this work was the wish to generalize this concept to infinite sets. So that's where the new part starts. An attempt had been made by Paul Hermann Zishang. There is a book where he said, well, let's say I have a set X, and let me define the intersection numbers as before. It's the count of the vertices of the triangles. And it works. You can fill 250 pages, as he did. But one thing fails in regards to this approach. Even though there are many beautiful algebraic facts that can be established, what does not work is duality. Because if we consider the group case, taking X to be an abelian group, such as integer numbers, then the dual group will be the circle, S1, right? Functions periodic on a segment can be expressed as Fourier series, and so the dual of a circle is integer numbers, the dual of integers is a circle. And so we can define a scheme on Z, but not on S1, because the space is uncountable, so we cannot count. So it does not quite work. And slightly more generally, if we take X to be an abelian group, let's say it's countable and discrete, such as integers, then the dual is uncountable and compact. And if the group in addition is periodic, meaning that every element has finite order, then the dual group is zero-dimensional. And so this approach does not work, and having realized that, we give the following definition. Of course, we replace the count with a measure. So let's say there is an arbitrary set with a sigma additive measure. We partition, again, X cross X into classes, measurable sets, at most countably infinitely many. So we have to postulate that the measure of y's such that xy is in Ri is finite, otherwise things cannot be proved. R0 is a diagonal. Again, there are symmetry relations. The transposed relation is a part of the partition, and then there is the count of triangles, except that now we do not really count the triangles. We compute the measure of these such that xz is in Ri, zy in Rj, and call that Pijk. So if by definition this does not depend on xy but only on k, then we call them intersection numbers. So this was the starting point of our work with Maxim Skriganov that was released fairly recently. We call X a commutative association scheme. And what we tried to do was to develop a theory of such schemes, and some parts of it we managed to complete. Well, we can argue about classification of association schemes in general. So if the measure of x is finite, and then the measure of a point is positive, then that's the classical case, discrete finite set. If the measure of x is infinite, but the measure of a point is finite, so that's like integers, so it's a countable discrete set. If the measure is finite, but the measure of a point is 0, those are compact spaces and compact groups in particular. Their duals are integers, such as a circle. And then finally, if both the x has infinite measure and the measure of a point is 0, a good example is locally compact abelian groups, and there are other examples. Right, so let me see what I have. The only thing I would like to highlight is what happens to eigenvalues. So there we had orthogonal polynomials, but now we will have something else. And this is perhaps the only thing that I wanted to mention in some detail in this talk. But, well, we can do something for adjacency algebras of those association schemes. We can define them in a natural way. Namely, we take chi I to be the characteristic function of the ith class of the partition, and then we define, so the adjacency operators, those were our matrices, A1, A2, and 3. They are now operators that act on the Hilbert space L2 of x. And AIF is characteristic function times f integrated over this set. And then the spectral theorem gives us a decomposition into eigenspaces in the Hilbert space, and the operators, the adjacency operators, can be expanded into a linear combination of those projectors. Now this sum is infinite, so we have to be very careful about what this means for operators, what kind of convergence we are claiming here. Topology begins to play a role, and until we define a topology that supports relations of this kind, we cannot really claim much. And I should put a disclaimer in advance. We do not know how to do this in the most general case. We do not know what has to be required of the space, but we can do this for infinite abelian groups. So then it becomes quite rigorous. And another major question is, when are the projectors indeed? When are they contained in the same operator algebra? When can we invert this relation? Even after we have established the needed convergence, whatever that would mean. We can do that again for schemes on infinite abelian groups. So abelian groups come in two varieties. The first is connected groups. A connected group, such as the real space, the first thing that comes to mind, but in fact there are hardly any connected abelian groups, infinite groups, right? Well, connected abelian groups in general. In the compact case, they are the tori. In the locally compact case, they are direct products of any number of copies of the real numbers and the torus, and that's it. There are no more connected abelian groups. And a claim is that they really do not support association schemes in our definition. So we go away from connected, and it takes a little while to realize that what we need to look at are not only disconnected groups, but groups that are totally disconnected. Totally disconnected, that means that connected components of the points are the points themselves and nothing else. Such group is zero-dimensional as a topological space, and the topology is defined. This is the base of neighborhoods of the identity element of the group, and it is defined by a nested chain of open subgroups, right? And then by shifts we can define the neighborhoods of any point in the group. The subgroups are of finite index. So this is very, very classical. The Cantor set or Cantor type groups give the primary example. So this is Z2 taken countably many times, p-adic integers, and there are slightly more general examples of this kind as well. This topology is metrizable, and interestingly, it is metrizable by non-Archimedean valuation. So we have those subgroups, they become balls with respect to this valuation. And those balls are now closed, so the subgroups are open and they are closed. Sometimes they even say clopen. So yes, these things happen. And so we can think of the subgroups as of balls with respect to this metric. And this is the picture of my zero-dimensional group. So this is the outer group, and then shrinking balls. all the way, go forever, and at infinity they reach 0. So that's how the group is arranged. Well, there are a bunch of results in this work. Perhaps the most interesting is that we can define translation schemes on zero-dimensional topological abelian groups, such as counter-type groups, Vilenkin groups, p-adic integers, p-adic numbers, and so on. And there are a number of links to harmonic analysis, briefly mentioned here. We can compute eigenvalues, we can compute intersection numbers, those Pij, But let me comment a little bit on the construction of eigenvalues. Because what happens with the eigenvalues, yeah, with 2-3 minutes I'm done. What happens with the eigenvalues, in fact, they have many properties of wavelet-like systems. And perhaps this is the link of combinatorics and harmonic analysis that I wanted to highlight. So we take a subgroup, xj, and we observe that our entire group can be partitioned into the cosets of this subgroup as shown. So then we replace a function f, the L2 function, even locally summable function. We replace it by the approximation on the coset of the subgroup, and then this approximation, this is one of the prominent steps in the Littlewood-Pelly theory, in the multipliers theory in harmonic analysis. So this approximation, so we replace the function by its expectation on the coset. It can be expressed as a convolution operator, integral operator, and then we consider the difference of two approximations between the difference between ER and ER attached to the radius, which is the next radius after R. So this difference, of course, has links to well, if we call the function now a random variable and use the language of probability theory, then you readily recognize the martingales here, because what we are doing conditional expectations. And it is well known indeed that this approach is in many parts equivalent to martingales. Burke-Holder inequality is a famous example of this approach, of this connection. All right? And the theorem that we are making is that we are proving is that the eigenvalues of the scheme as defined on this group are in fact given by the evaluations of the kernel of this integral operator, the difference of the two approximation operators. Very well. What can we say about the kernel of this operator? This is an example for the counter-type group computed if the index of each subgroup in the previous subgroup is p, so we have this function of 3 values, reminiscent somewhat of Haar wavelets. But slightly more generally, we can say, well, this now the notation becomes somewhat heavy, I won't have a chance to explain it. But the kernels of these integral operators can be expressed in a familiar form of these reproducing kernels. And the function system of this kind, it forms an orthogonal basis in the L2 space on the group. And it has all the properties of multi-resolution analysis, except perhaps the self-similarity property. So we cannot say in general that there is a function that generates everything by dilations and translations. Self-similarity is present when xj plus 1 has index p, prime p, in xj for all j. So those balls, they go down by equal steps. And then we do have self-similarity. Otherwise we don't. But otherwise we have all the properties of an MRA, and there was a paper by Girardi and Sweldens somewhere in '95 that called this second generation wavelets. And they spoke, in general, they didn't have many examples of those second generation wavelets, but this is perhaps one example. These functions seem to be new, and we've been looking at them with Weishran here, proving some simple things, completeness, pointwise convergence, but well, this is a developing story. So this is a somewhat new link between association schemes and algebraic combinatorics on the one side, and harmonic analysis, replacing orthogonal polynomials with wavelets. And I'll stop here. Thank you.
Let's thank the speaker again. And So we have about 15 minutes break until 9:45, the next talk will start. But just as an announcement, those of you who have not registered or have registered but did not pick up your name tag, you can do so downstairs, first floor, main entrance of the building. We have the registration tables there, so just